Section 3.3 Subspaces. Well, we have seen what a vector space is. Remember, it's a set. In this case, it was real numbers, order a sequence of real numbers uh, that they satisfy certain properties under two operations, the sum and scalar multiplication. That we call that Rn. So now, based on that, we're going to start in this section what is a subspace. So first, any subset W of Rn is a subspace of Rn if W itself is a vector space. This is, it satisfies all the properties for sum and scalar multiplication. So remember that a set SET is a collection of anything. A subset is a sub-collection inside that set. So if we have the vector space Rn, any subset of it is going to be a subspace if that set itself is a vector space. This is satisfies all the properties for sum or addition and the scalar multiplication that we have seen for vector spaces. Example. Consider Act 3. Consider R3. As the vector space. And consider the subset from R3 that is defined in the next way. Is going to be W equal to all the elements or vectors X such that X is equal to X1, X2, and 0, where X1 and X2 are real numbers. So this is a subset for R3. Maybe you are a little confused about the notation. This is W is the subset of all the elements or all the vectors in Rn, in this case R3, such that they have this form. X1 and X2 can be any real number, but the third coordinate must be 0. So this is a subset of R3. We could prove that W is a subspace. How could we prove that? Well, we would have to verify that all the properties that we have seen before for the addition or sum and the scalar multiplication for vector spaces, they are true, they are satisfied. But trying to verify those properties every time, each time, might be tedious. So we have another way to verify that. But by the way, graphically, what is this vector space in this context? What is this vector space? R3 is the three-dimensional plane. I mean, the three-dimensional space, I mean. We have the x-axis, the z-axis, and the y-axis. But well, in this case, I think we have x1 and x2. Well, it's okay if I use x, y, and z. So notice this, all the points that you can find here, they are elements, or they represent, they can be related to one vector from R3. So we can say graphically that R3 is the three-dimensional space. But what is W? Notice if the last coordinate is 0, that means we don't have any coordinate for the, well, I mean, the coordinate for the Z axis always is 0, right? So that means that in this case, the subset W is all of this, region in pink. All of this region, that is W. So all the plane XY is going to be W. So we could prove that W is a subspace. But again, we would have to verify all the properties for addition and sum, but we don't have to do that. There is another way to do it easier. Theorem. W a subset W of Rn is a subspace if and only if we can verify three conditions. Number one, the zero vector is in W. Number 2, x plus y is in W for xy in W. And number 3, c times x is in W for x in W. C is a real number. So this only means that it has the zero vector. How can we verify whether a given subset from Rn is a subspace? First, it must have the zero vector. 2, close under the addition or sum. I mean, if you take two elements, x and y, in W, and you do the sum must be in W as well. C times x, close under scalar multiplication. So if we have a subset of W from Rn and we verify these three properties, then W is a subspace. If only one of these fails, W is not a subspace. Examples. Determine if W equal to the elements A, B such that A plus B is 0. You have to read this as W is equal to the set of the elements A, B such that these 2 points, you have to read this as such that A plus B is equal to 0. Is a subspace of R2. All right, so we have to verify the three properties. First, does W have the 0? Notice, if the 0 is part of W, then the sum of the two of 0 plus 0 must be equal to 0, and that is the case. So the reasoning is this: since 0 plus 0 is equal to 0, take this as A and this as B, then 0, 0 is in W. Why? Because W has the elements such that the sum of the two elements A, B is equal to 0. If you take A equal to 0, B equal to 0, the sum is 0. So 0, 0 is in W. But 0, 0 is the 0 for R2. 0 vector of R2. So the property number 1 is true. Number 2, is it closed under sum? Is W closed under the sum? So what do we have to do here? We have to take two elements from W. So I'm going to choose two elements from W. Suppose A1, A2, and B1, B2 are both in W. Yeah, we take two elements from W, and remember W is this, the elements A, B such that their sum is equal to 0. So we take these two elements. Now I'm going to do the addition. We sum A1. No, I'm sorry. First, if these two elements, they are in W, then the sum of A1 and A2 is what? A1 plus A2 is equal to 0, right? Because A1, A2 is in W. That is the property that defines W. And the same for B1, B2. B1 plus B2 is equal to 0. Now, from these two equations, add the two equations. This implies A1 plus A2 plus B1 plus B2 equal to 0 plus 0 is 0. But this is equal to what? This implies, notice that, if we arrange this, we have that A1 plus B1 plus A2 plus B2 is equal to 0, right? I mean, A1 plus B1. I only modify the order of the sum. I can do that because these are real numbers. And the sum here, the sum is the sum of the real numbers. So I can express this as A1 plus B1 plus A2 plus B2. But this implies that A1 plus B1 comma A2 plus B2 is in W, right? Because W has all the elements in that form. All the elements A, B such that the first element plus the second element is equal to 0. So this is the first element and this is the second element. So then this implies that A1 plus B1 comma A2 plus B2 is in W. But this is only what? This is only the sum of A1, A2 plus A B1 B2. This is only the sum of these two, right? Because remember, how do we do the sum in R2? The sum is made only the first element plus the first element. A1 plus B1, comma, A2, and the second element plus the second element. So this is only the sum. This proves that the sum is in W. So it is closed under the sum. So it is true. Yes and yes. What is the last one? Is closed under the scalar multiplication. Is it closed under scalar multiplication? So the same. Assume we have one element A1, A2, or we can use in this case AB. AB is in W. Then A plus B is equal to 0. And if you multiply here, if you multiply this equation at both sides, we have times C, we have C times A plus B is equal to C times 0 for any number, for any real number C. So this implies that CA plus CB is equal to 0, right? And if CA plus CB is 0, this implies that CA, comma, CB is in W. CA plus CB is in W. Because C times AB is equal to, remember the scalar multiplication is only multiply this time this and this time this. So this is CA, comma, CB. So this proves what? That the scalar multiplication is in W. Okay? So yes, it is closed under scalar multiplication. Is it closed under scalar multiplication? Yes. So it satisfies the three properties. So W is a subspace of Rn. So W is a subspace of R2. Now, one example of something that is not a subset that is not subspace. Example. Show that W equal to the vectors AB where either A is 0 or B is 0 is not a subspace. If this is not a subspace, it's going to be enough to show that at least one of these three properties is not true. If you can find that only one of them fails, then it is not a subspace. I know they can fail more than one, but if you can find only one that fails, it's not a subspace. So Notice, choose the elements 1, 0, and the element 0, 1. Are these two elements in W? Yeah, they are, because this is the set of all the elements AB, where either A is 0 or B is 0. One of the two is 0. So all the elements that they have, this one 0 or this one 0, they are part of W. So 1, 0, I choose 1, 0, and B as 1 here, and these two elements are part of W. But notice what happens when we do the sum. Then 1, 0 plus 0, 1 is equal to what? 1 is equal to 1 plus 0. 0 plus 1 is equal to 1, 1. This is not in W. Why not? Because here the two elements are 1. We don't have one of the two zeros, so this cannot be part of W. So the condition number 1 fails. This one, number 2, it's not closed under the sum. Then W is not closed under the sum. So then W is not a subspace. Not a subspace. So it's enough to show that one property fails. Okay? But if you want to prove that this subset is a subspace, you have to show that the three properties are true. So be careful with that. Now, span of a subset. If we have B1, B2, and so on, up to Bn are vectors in Rn, then A1, B1 plus A2, B2, and so on, up to An, Bn, is called a linear combination of B1, B2, and so on, Bn. For some scalars, A1, A2, and so on, up to An. So, what is a linear combination? Linear combination. You need to have a finite amount of vectors from Rn. And if you can do the sum, if you do the sum where you multiply by some scalars A1, A2 up to An, then this is called a linear combination of the vectors B1, B2 up to Bn. For example, in R2, take, for example, B1 equal to 2, 3, and B2 equal to 1, 1. These are two elements in R2. Remember, R2 is all the set of these pairs in this way, order pairs. So one possible linear combination is I can use 5 times 2 comma 3 plus 6 times 1 comma 1. So this, notice, this 5 times b1, 6 times b2. This, that looks very simple, yeah, this is a linear combination. If you want to do the operation, no problem. In this case will be multiply the 5 times 2 is 10, 15 plus 6 comma 6, and then you add, is going to be 16 plus comma 21. So notice this is a linear combination of this in the result. You see? So that is a linear combination. But notice how I show these scalars 5 and 6, but I can choose any number that I want. A1, A2, AN, the coefficients multiplying the vectors can be any real number. Other possibility could be, for example, choose -2, 2 comma 3, plus 4, 1 comma 1. You see? And this is -2b1 plus 4b2. You see that? But again, this is only a linear combination. Now I chose as coefficients -2 and 4. You see that? -2b1 plus 4b2. You can choose any coefficient that you want, any numbers. And with that, you will have, yes, a linear combination of b1, b2. The only thing that is not changing in this example is b1 and b2. Once you fix this, we have, and you change the coefficients, we can have several or infinitely many linear combinations. If you want to solve this, no problem. It's going to be -4 comma -6 plus 4 comma 4 equal to -4 plus 4 comma -6 plus 4 equal to 0 comma -2. So the result of this linear combination is this. Both are linear combinations of the vectors b1, b2 defined as this. All right. So now we understand what a linear combination is. We have the next theorem. Given vectors, any finite amount, b1 and so on up to bn, in R2, I'm sorry, Rn. Any finite amount, then oh, by the way, these two numbers n and n, they might not be the same, so I can use here bn, for example. So then the set of all possible linear combinations of B1 and so on up to Bm is a subspace of Rn. So this is saying to us that once you choose a finite amount of vectors in Rn, where Rn can be R2, R3, R4, and so on, any finite amount of vectors, all the possible linear combinations you can create, those or that collection is a subspace. Proof. Oh, by the way, this set has a name. This set of all the possible linear combinations of B1, B2, and so on is called the subspace span by B1, B2, and so on up to Bn. Yeah, I'm saying here that this set, this subset, or this subspace is called, it has a specific name. It's called the subspace spanned by B1, B2, and so on up to Bn. It is denoted like it can be denoted by SP of B1, B2 up to Bn, or SP of S if S is that set, B1, B2 up to Bn. All right. Notice I'm going to prove that the span of B1, B2 up so on is a subspace of Rn. Now, I'm sorry, remember that these two numbers are descent and descent, they don't need to be the same. I mean, it's only a finite amount. So, but how can we prove this? First, does SP have the zero? Can in other words, can I find a linear combination for any vector such that I have the zero? Yes, it's very simple. Just choose all the coefficients, A1 equal to A2 equal to A3 and so on, all of them equal to AM equal to 0. Only choose the 0 and you will have 0 times b1 plus 0 times b2 and so on up to bm, and this is going to be only the 0 vector, right? Remember, this means 0 vector. I mean, this is only the vector 0, 0, 0 m times it is 0 vector, m zeros. So the 0 vector is a linear combination of these vectors b1, b2 up to bm. Yes, always it is, right? All right, so is it close? I mean, does it have the 0? Yes. Number 2, is SP b1, b2, and so on close under sum? Is it close under the sum? I need to have two linear combinations. Notice, consider two linear combinations. Consider two linear combinations. Not necessarily different. For example, A1, B1 plus A2, B2, and so on up to AM, BM. And another combination, B1, B times B1, B2, B2, and so on up to BM, BM, and then do the sum. If you do the sum for this, notice I can factor the B1 from each. This is one property from vector spaces. So this implies, if you do the sum, this implies that we have A1 plus B1 times B1 plus A2 plus B2 times B2 plus and so on up to AM plus BM, BM. So what do we have here? We have, these are coefficients. So again, I have another linear combination. So the sum of two linear combination is still a linear combination. So this proves that the sum, then the sum is in the span. So is close under the sum? Yes. Finally, is SP, B1, B2, and so on, BM close under scalar multiplication? It is close under scalar multiplication. So again, consider one linear combination, A1, B1, and so on, AM, BM, and see a real number. If you do the multiplication, C times this, from the properties for vector spaces, I can multiply the C times all the elements in the sum. So this becomes C A1, B1, plus C A2, B2, and so on. C AM, BM. So again, I have, notice how I have other linear combination because C is a real number, A1 is a real number, so the product is a real number. A coefficient times B1, another coefficient times B2, another coefficient times bm. So yes, I have another linear combination. Then the scalar multiplication is in SP. So this proves, so the three properties are true. So what can we conclude? That the span for any amount of vector from Rn is a subspace. So it's a vector space, always. Is that okay? Examples. Given the vector b equal to 1, 2 from R2, the span of B is SPB is equal to A times B for any real number A. Some elements in SPB are, choose any, assign any value for A. For example, 1. 1 times 1 comma 2 is 1 comma 2. This is one element from the span. 2 times 1 comma 2, 3 times 1 comma 2, and so on. 2 comma 4, 3 comma 6, and so on. So we have infinitely many. In this case, notice how we have the possibility to have only one vector. No problem with that. We can consider only one vector, and we still, this SPB is going to be still the span, and it's going to be a subspace. Example. This was one example, part A. Part B. Given the vectors B1 equal to 1 comma 0 and B2 equal to 0 comma 1, then the span of B1 comma B2 is the set of all the elements A1 B1 plus A2 B2 such that A1 and A2 are real numbers. So in this case, I want to show you graphically what is the meaning for this. Since these are elements from R2, so remember that graphically, this is the Cartesian plane. So in the Cartesian plane, what is this subspace graphically? Well, remember that I can identify these two vectors as points. So this is going to, let's say that this is the point 1 comma 0, and this is the point 0 comma 1. Then if you consider all this the sum of these two, remember the sum of two vectors is the diagonal of the parallelogram created by this. So in this case, the span of B1, B2 is only a line. Because the sum of any of these two, A1, B1 plus A2, B2 is going to be only this, is going to be, there are going to be points in this line. So in this case, the span is only this line. That okay? Now, other example. How to verify whether we have that an element is an element, a given vector is an element of the span. Example, given the vector B equal to 3, 2, and the vectors B1 equal to -1, 1, and B2 equal to 4, 5. One question, is B a member or an element of the span of B1 and B2? Some of these exercises are in the homework, so please pay attention as to how to compute this. You will have to create a system of linear equation, but you already know how to solve them, right? We have seen that before. So if B is in the span for B1 and B2, then B must be a linear combination of B1 and B2. Then there are scalars A1 and A2 such that A1 B1 plus A2 B2 is equal to B. Or in other words, A1 times, what is B1? -1, 1, -1, 1, plus A2 times, what is B2? 4, 5. 4, 5 is equal to B. What is B? Is 3, 2. And from the properties of vectors or matrices, multiply, we have -A1 plus 4A2 must be equal to 3. A1 times -1, -A1 plus A2 times 4, 4A2 equal to 3. You see the first elements. This is only from properties for matrices and multiplication and sum. And then A1 times 1 is A1 plus 5A2 should be equal to 2. You are going to end up in this kind of exercises with a system of linear equations. A system of linear equations, all right? And what you have to do, you have to solve it. If it has solution, then B is in the span of B1, B2. Otherwise, B is not. In this case, I can solve the system. I can add it to equations. Notice. Again, you don't have to solve this in the exercises from WebWord. Of course, you don't have to necessarily solve this manually. I recommend to use the techniques on this that we have seen before, and especially use some web page or software application to compute the solution for systems of linear equations. No problem with that. So, but in this case, I'm going to do with the method of elimination. I add these two, add both equations. So we have this negative a1 plus a1, they cancel out. 4 plus 5 is 9a2 is equal to 5. So for a2, we have 5 over 9. Then back substitute this result into either of the two equations. I'm going to do it in the second one. Substitute into equation 2, and we have a1 plus 5 over 9. 5 times 5 over 9 is equal to 2, and this implies a1 plus 25 over 9 is equal to 2. So this implies that a1 is equal to 2 minus 25 over 9. And this implies that 18 minus 25 over 9, that is a1. So a1 is equal to negative 7 over 9. So yes, it has solution. So then if you use a1 5 over 9 times b1 plus negative 7 over 9 times b2, you're going to have b. So this is 5 over 9 times negative 1 plus negative 7 over 9 times 4 5. This should be equal to 3 2. You can verify that if you want. If you do the operations, you are supposed to verify this. This is not 4 over 5. This is 4 5. I'm sorry. 4 5. It's a vector. All right. So in this case, yes. Then since B is a linear combination, of B1, B2, then B is in the span of B1 and B2. So yes, it is part. Is that okay? All right. That's all by now. See you later.